In this session, we are going to discuss some additional principles of morphology, or the form that different electrodiagnostic potentials take. These basic principles apply to motor nerve conductions, sensory nerve conductions, the EMG voluntary potentials, as well as abnormal potentials. We will concentrate primarily on the motor nerve conduction waveform, but again, all of the principles apply. I'll start with a little bit of a detour. Pictured here are the Riders of Rohan from the Lord of the Rings trilogy, one of the most climactic scenes of the series, when all appears lost and the forces of evil are about to defeat the forces of good, and at the last possible moment the Riders of Rohan come storming across the hilltop to save the day. When you look at this picture, what you see is not 7,000 people and 7,000 horsemen. You see a mass of humanity, a mass of forces. It looks more like one thing. It's difficult to separate the individual components. And in fact, I think that's a pretty good analogy for what we see in the EMG lab when we measure potentials. So if we start by returning to our motor unit X potential, which again looks something like this. The motor unit X potential is the mass of the Riders of Rohan, and it consists of, if we could measure them, which we can't, a lot of very tiny individual X potentials, each one attributed to a motor unit and activation of a single muscle cell in this case. And there's some dispersion of those potentials, and the morphology may be slightly different for each of those potentials. But all those potentials together are algebraically summed to form what we see on a recording on the EMG screen. So a couple of dynamics are important to keep in mind. One is that there's a bandwidth of speed of conduction for each of these potentials. I would need to draw one over in this area to really express the true bandwidth. And that bandwidth has a direct correlation to the width of the ultimate measured potential. Another important principle is the onset latency of the fastest population of fibers, or the fastest population of depolarizing muscle in this case, corresponds to the onset latency of that potential. So that's also an important fact to keep in mind. So that's issue number one, is that all potentials are the algebraic sum of their component potentials, which we don't actually see during the exam. The second analogy I'd like to draw relates to this human pyramid, and you could think of this as a human potential, if you will, but it is 6 people high. If we assume that each one of these people was 5 feet tall, foot to shoulder, just to make the math simpler, then we really have a human potential in this case of 6 levels times 5 feet each, so that potential is 30 feet high. And if we were to measure from the leftmost aspect of one of the white trousered people on the base of the pyramid all the way over to the rightmost person, we might find the base of that pyramid is about 12 feet. So that's our normal human potential. Now, there are actually 3 things that we could do to this potential, or these people could do to their potential to change it. The first thing would be for everyone to move to the right. If all the people on the base of the pyramid took tiny baby steps over to the right side of the screen, and they managed to hold their balance and keep the pyramid completely intact, and they move 10 feet or so, what you would find is this pyramid would be physically moved over to the right, but it would still be 30 feet tall, and it would still be 12 feet at its base. So that principle is that the movement, or by way of analogy to the EMG, slowing of fibers, if all the fibers move the same amount, if they all slow to an equal amount, then the morphology of the action potential doesn't really change. You still have a 30-foot high, 12-foot wide pyramid. The second thing that might happen is, let's say, for example, that the 6 people on the very top of the pyramid decide to get off and start a pyramid right next door to the parent pyramid. So we're going to lose 2 rows, 5 feet each, that's 10 feet. So our 30-foot pyramid is going to become now a 20-foot pyramid. It's still 12 feet at the base, but those 6 people now have stepped next door here, and very close to its parent have created a second pyramid. So if we measure this human potential, that potential is now 20 feet high, and it might be 20 feet wide because we have this extra contribution from the secondary pyramid. So this would be an example of differential slowing or differential movement of our people in the pyramid. And note that although we have lost height of the pyramid, we've gained width, and we have not gotten rid of any people. We still have the same number of people contributing to this pyramid. They're just spread out. And then the third thing that might occur is, let's say, for example, that the 2 people on the very top of the pyramid decide they're going to dismount. So we lose 1 layer, 5 feet tall. So our pyramid is now going to be 25 feet tall. And it's still going to be 12 feet wide. And those 2 people at the very, very top, they walk all the way over to the right side of the plaza, and they make a tiny little pyramid all by itself over here. In this case, if you were to measure the width of that human potential, it's actually not 12 feet. It has to incorporate all the members of their team, so the width of that potential might be 50 feet. So 3 different cases, equal slowing of all the members of the team, differential slowing, and then extreme amount of slowing for a subpopulation of people in the pyramid. So how does it relate to nerve conduction studies? It's probably become apparent to you if I redraw my population of fibers here, and I'm trying to draw them much the same as I did to the left side of the screen. They're all slightly different. And then suddenly we get to the fibers that were on the top of the pyramid, and they're a little bit slower. Not so much to be entirely separated, but enough to kind of start to set up their own pyramid just to the right of our existing pyramid. So in that case, what we'd see is much like we did in the case 2 below. We're going to see a potential that is going to be lower in amplitude because it's lost some of its contributing fibers, and it'll be slightly more spread out. So still a motor unit X potential, but our amplitude has decreased and our duration has increased. And that phenomena of decreased amplitude and increased duration is the phenomena of temporal dispersion, or dispersion of the potential over time. In the final case, you could imagine if these 2 potentials acted more like case 3, where they walk over to the other side of the plaza. I won't draw those out, but just imagine I pulled both of these potentials even further off to the right and separated them out. In that case, what we would get is something that might look like this. Again, we've shortened our pyramid. Might have more of an irregular shape. And then we have two renegade acrobats that now are way out to the side here, form their own little potential. And that's far enough out that it has separated from the parent potential altogether, and this phenomena is typically called a linked potential or a satellite potential. So that is some basic principles of electrodiagnostic recording of potentials. A couple of real simple clinical examples. So in the case of temporal dispersion, a disease state that might cause this differential sort of slowing, where you've got more slowing in some fibers than others, and you get true temporal dispersion. You see that in disease states like Guillain-Barré, where you have focal demyelination, and the demyelination is patchy. You might see case 1 where we just see a movement of the potential over to the right. Everything slows equally in those disease states that cause more or less equal demyelination in a disease state like Charcot-Marie tooth. So again, 3 takeaways here. 1, potential is a sum of the individual parts and sum algebraically. 2, the onset latency of the potential relates to the onset latency of the fastest population of fibers. And 3, any process, and we'll discuss these processes in more detail in future sessions, any process that increases the variation in conduction or increases the slowing of conduction of these fibers differentially will create the phenomena of temporal dispersion without actual loss of axons.